Hello, welcome back. So we're gonna continue working on our 3D rotation projects. So as you can see, we try to simulate the perspective projection, but it's not working properly. But we can at least see that the object is there and it is rotating. Just it's being cut or something. So to solve the perspective projection, it seems that we just need to translate into z-axis so that it can be visible with the camera, because it's like on top of the camera, which is kind of invisible. So to do so, we actually need to translate along the z-axis. We can do that with the matrix multiplication, uh, with the model view matrix. We can append the okay translate along z along negative z-axis, right? Z-axis to be visible in the frustum. Okay, so to do so, we just need the model view matrix that we already built, and we need a multiplication of um, of um, um, of our translation to the previous one. So let's take the translate, which we already have in MVGS, and we want to translate along minus z-axis, and let's translate along -2, right? And which we need to multiply with the previous model view. Okay, so let's see what we get. Yeah, oops, let's try to rotate. Now it's quite white because we implemented this depth coloring, so that's why when the depth is too, I mean back, behind, it's more white than when it is closed. So let's try to zoom a bit, because we set the depth naturally is to be -2, so it's automatically being very white, right? um, okay, so the perspective projection is working properly. What if we want to try to visualize it? We just need to change the coloring here. Okay, let's set back our incoming color to see it properly. Okay, now we can see the object is rotating. We need the hidden surface removal, and yeah, it's rotating perfectly. Okay, but using a rotation matrix. And let's try an object, and then we move to our height map coloring. Let's take the AI. Yeah. Yeah. Okay, let's scale it a bit. Yep, so it's working. So what we need to do is to, let's set constant of the z, right? So that maybe we want to control it. Actually, I think it's not necessary to control it, but yeah. But let's just set the constant here. Let's set it's like model dot translate z. Okay. Let's give the constant of -2. I already did it. Okay, yes, I have it here. Okay, let's save, and yeah, everything is still working. Perfect. Okay, now coming to the second part of our objective is height map coloring. So the higher points will be colored in red, and the lowest one will be colored in green, and it should be interpolated so that the mid one will be coloring with white, with yellow. Sorry. Mm, okay. So to do so, we first need to work in the fragment shader. Okay. First of all, let me write here height map coloring, and to do so we need the GL dash frag color, and we need the vec4. So what we need is a GL dash code, frag code, and we take the Y value, we put it into the red. If the Y is high, we get more red color, and if the white is if the yes, but there is a mistake, right? Because the frag color give this, it doesn't give us the normalized screen coordinate, it gives the real screen coordinate, so we have to divide by the width of canvas, no, the height of canvas. Yeah, I think it should be the height of the canvas, right? Okay, let's try float. We take a float, we set it to red, which is equal to the frag gel frag y. Let's set red here, and which should be divided by canvas height, if I'm not mistaken, but we have to declare this one as a uniform uniform variable to get canvas height, right? Okay, which is a uniform floating point and canvas height. Okay, we get it from outside directly from the inside the fragment shader. Yes, fragment shader. So let's finish here, and then we're gonna pass it. So if we get it, we set okay, so we set it here, and here we need just to do 1 minus the red, so we get the green, and the blue should be 0, and the opacity should be 1. Okay, okay, let's try to save and try to pass the canvas width, no, the canvas height instead. Okay, okay, let's declare here var canvas height location, right? Okay, let's do it here. okay, get the location of the uniform canvas height in the program. Okay, let's set var. Actually, we already declared it. Canvas height location equals to gl dot get uniform location from the program, and the name is canvas height. And as soon as we get it, we passing the canvas height value into the fragment shader, right? So we did gl dot uniform, it's not matrix, it's uniform, uniform 1 and floating point. Yep, we just need canvas height location and the value which we need to parse to float, and it should be canvas dot height, right? Canvas dot height, if I'm not mistaken. Okay, let's try. There is something wrong. Operand, no operation exists that takes a left. Okay. I think the problem is here. Yes, it's working. Now we can see the top one is more red and the below one is green. And let's try to see one of the object. AI. Yeah, we can see that his head is more red and his foot is more green, and we try to interpolate. Okay, let's try to flip, and when we flip we see his legs become more red than his head. Okay, so let's try to see the problem with the yellow. Okay, Let's try something. If the red is greater than um, is greater than 0.75, if the red is less than 0.75 and 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 is greater than 0.25, or let's say 30, all right, to get the yellow, 70. Okay. So if the red belongs to this range, we can just give yellow. Okay, let's try. There is, okay, let's try AI. Oh, it's it's not beautiful to see. Seems so. Because we interpolated already, right? So okay, and the more we zoom out, the more problem we get. Okay, what if we get this thing from here? Okay, we just pass the normal coloring. Okay, but we try to do in a shader, vertex shader. While passing the color, okay, we do the V position Y, V position Y. I think it's already in the normalized device coordinate. But it's minus, right? Sometimes it goes to minus. So sometimes it goes to minus, so we need to add 1 and we divide by 2. Because it's between 1 and minus 1, we want to shift it, so we add 1, it will become from 2 to 0, right? 1 plus Vy, and then we divide by 2. And we divide by 2. And then we get the red that we wanted, and we pass this one into our out color. Our out color will be this one. This one. And let's comment that one and see if it works. Okay. Oh, divide by 0.2. Okay. Interesting. Let's see the AI here. Oh, I think it's working, but quite bizarre. And I guess if we flip it, it will not change. I think we're just gonna keep it into the fragment shader. Okay. And let me delete that one. Okay. Let's stick to this one. We couldn't interpolate to get to yellow yet, so it's just red and green interpolated. Okay, let me check the timing. We already did 20 minutes. Okay, perfect. Correct, right? So everything is good for now. The goal is to work on our trackball, right? So to do the trackball, we need mouse down event handler, mouse up, and on mouse move, right? So to do so, let's first do some stuff here. Okay, window that on mouse down, we take on mouse down, and window on mouse up, we take on mouse up, and window on mouse move. And this one we take on mouse move. All right. So, and I would like to point that, okay, we will reach to that, but let's declare those function. Okay, function on mouse down, we take an event, function on mouse move, we take an event. Perfect. So on mouse down, we have to know also that if the mouse is here, then we collect the coordinate, right? And we want to do as if when someone click, then they can start moving the object, and when they unclick, we stop the rotation, right? So we want, because if we don't implement that, someone just go with the mouse, the object will start moving. It's like you cannot really control what you want to do, right? So that's why click, then we know that we can start rotation. Unclick, then we stop the rotation. For that, we need a flag that shows that, oh, we clicked, oh, we unclicked. Okay, so to do that, let's declare some variable up here. We will need them. Trackball parameters. Okay, let's declare dragging, which will be false by default, and we need also prevex. Okay, prevex, which is like the first click that we clicked, we took the coordinate, right? So every move we will calculate the quaternions based on the previous. So we're going to update the previous. So if we calculate the quaternion of this move, then the previous will be this point. So then if we move here, the previous will be, we calculate the quaternion, the previous will be this one, right? So prevx and var prev_y. What else do we need? We need a quaternion rotation, var quaternion rotation, right? We need quaternion rotation, which will be something like a new float array, right? Yeah, and we need also another quaternion which will behave like the increment of the, for instance, we want to rotate from here to here, so but we have to divide it to have the interpolation, right? So we rotate here, 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 here. So we want the quaternion to be the increment of each. So the quaternion increment will be how much rotation we need to have from the quaternion rotation till here. And if we reach here, how much we need. So the quaternion increment will get what we need, and then we just multiply with the quaternion rotation. So we get a final rotation from the original point till what we wanted. So quaternion increment, which should be also a new of float 32, anyway, yeah, 32. Okay, and we have to initialize all of them with identity quaternion. So quaternion is initialization to identity. Okay, quaternion rotation. Oops, the first value, we consider our first value here is the real part, but some people decide to do it differently. And oops, okay, here is 1, 2, 3, 0, 0, and 0. That's a first rotation. I mean the quaternion rotation. Then we need the quaternion increment also. Okay, 1, 3, 2. Okay, perfect. We get some variable we want. If there is any, we're gonna put it later. So now, okay, let's implement our mouse down function. Okay, so on mouse down, first thing we need is our x location, which is e dot client x, and let y equals to e, which is an event, the event that we took, y, right? So we want it to happen, to take, so to consider this one as a previous, I mean our start point if we are inside the canvas, right? So to do so, we need to get the rectangle which will be our canvas. Okay, e dot target dot get it's get bounding, if I'm not mistaken, bounding client rect. If it's wrong, okay, it's doom rect. Okay, correct. So we're gonna check, oops, checking if we are inside the canvas. If x is greater or equal to rect dot because if x is inside, it means it will be greater than rec left. Yes, rec left is from the beginning of the screen on the left till the beginning of the canvas, which means if we are inside, x will be greater than that, and also and not only we should be inside, but also we shouldn't be outside from the right? So also x is less than rect that right, which is from the beginning of the screen till the end of the canvas. Okay, and we need also the y to be greater or equal to rect that top, which is from top till the beginning of the canvas, and y also should be strictly less than rect that bottom, which is from top till the end of the canvas from the bottom. Okay, if we are in that range, then we take our prev x equals to the x, and our prev y equals to y. So we consider it our first initial, points. So we take the dragging. We have to start the dragging, right? Dragging equals to true. I guess that's it. Mouse down. Now, if mouse up, we need to check. Okay, let x equals to e dot client x, oops, and let y equal to e dot client y. And if we didn't move, if x equals to rev x and y equals to rev y, then we um, in that case we set the drag to be false. Mm, there is one issue. Yeah, okay. Actually, we need to do that outside. Okay, but when it's not clean, we know that the quaternion increment shouldn't be changed. It should be the same. So we just need to initialize it back to quaternion increment should quaternion increment 0. Let me just copy from here. Quaternion increment should be the identity matrix. Identity quaternion. So okay, mouse up. Perfect. So, but one thing that we have to consider is that during the rotation, we want to cut, we want to divide the rotation so that we rotate, but we can do it based on timing, right? So when we are rotating, we calculate the quaternion increment per 20 or maybe 30 or maybe 15 milliseconds. Then we calculate the quaternion rotation. Then we combine with the the quaternion increment. We combine with the quaternion rotation. We transform it to matrix rotation, and then we push it to the vertex shader. Right? So what we have to do here is to determine the timing. So for that we need another variable here let's say var last time, okay, our last time variable here. So on mouse down, if we are inside here, then last time has to take something, right? Last time is date dot now. Give us in milliseconds. So now on mouse move, but I have to prevent also the default behavior of the click, right? For mouse down also I have to prevent that. Mouse up, let me just do it in case. Okay, so on mouse moving, that's where the magic will happen. Let's let x equals to let's take it directly from the device normalized device coordinate. Let's take current nbcx equals to, now that's where the thing is a bit tricky, but let's first declare our let right here, which equals to e dot target dot get bounding client right? So here okay, we know that let's get also let x equals to e dot client x and let y equals to e dot client y, right? So we know that our real x location will be x minus rec, because x has to be bigger than the left one, right? So I mean the padding of the canvas. So rec left, we minus the left, so we know the position inside of the canvas, right? But the position inside of the canvas is like based on the canvas width, right, of the x, but we want it into the device coordinate, right? We want it into the device coordinate, and but actually we want it to be unit length. So first of all, let's start like this. So we have to divide it by rec dot width of the canvas, width, but again we want it to be in normalized device coordinate, and that coordinate is 1 to 0, but we want it to be in 1 till -1, right? So what we can do for the x is that we multiply this one by 2, which become 2 0, and we just subtract -1, which become 1, and -1, because 0 minus 1 will be 1, right? Okay, perfect. So we get it here. We have to time it by 2, and the whole thing should be -1. So we get the current normalized device coordinate of the position of the mouse. Correct. Let current normalized device coordinate y equals to normalized device coordinate y equals to For the y is a bit tricky. Um, Actually, for the y also we have to do something like y minus, I like space here, which is rec dot top, yes, to be inside the canvas. Then we divide it by the rec dot height. Oh yeah, that height, right? Now we get into the range of 1 and 1, but we want it to be in the device coordinate, and this one is like y on the screen in the canvas is like from 0 to 1, right? But we want it from 1 to minus 1. So same thing should happen. We need to times it by 2, which yes, yes, yeah, yes, yes. Mhm. I think, yeah, it's 0 to 1 on the screen. We know that always on the screen it appears on the left corner, right? So it's 0 to 1. So if we times 2, this one remains 0, this one becomes 2. But if we do 1 minus 0, we get 1, but 1 minus 2, we get minus 1. So because our goal is to get 1 and minus 1, right? Correct. So let's go. Okay, so we have to do 1 minus this guy here. Okay, we get into the device coordinate. Okay, now if we get our device coordinate, what we can do now is to okay, we need now to decide the vectors from the previous. So we get the first point, the second point, I mean the point of the increment. So now we need to determine the vector so that we can calculate the quaternion. So let's say v1 equals to, let's do the projection, because we have to project on the sphere. If we don't project, we will have the length of the vector more than the sphere that's, I mean, illusion of sphere that's around the object. And we're gonna decide about the sphere to be, let's say, 2. And if we project on that, we have to get it on the sphere. Yes, because if it's far, when we calculate the the cross product, we're gonna get something more, a bit not correct. Uh, so yeah, projection on sphere. So the projection on sphere will take, so v1 will be the first click, which will be like a, okay, it will take the same thing, but let's say last NDC, normalized device coordinate, right, X, and it will take last NDC, normalized device coordinate, Y, and it has to return as the point X, Y on the coordinate and the Z on the sphere instead, I say coordinate. We're gonna declare the projection sphere later. Now let's just do, and it will be vec3 v2, which is equal to projection on sphere of current ndcx, current ndcy. Right now we don't have a last ndcx and last ndc. There is a problem because we don't know if the dragging is on, right? So we have to declare here something like this. But here okay, let last ndcx equals to we just need to replace this one by prev x. Okay, let me check the timing. Wow, 52 minutes. Okay, so to keep it consistent, let's say this one is prev ndc, prev ndc x, and let prev ndc y, which will take this one this one will be prev y. Yep, and this one will be prev ndcx, prev ndcy, right? Okay, but you know the problem again, when we are dragging, from which episode we start calculating the quaternion increment. So we have to decide about the timing, right? So let now equal to date that now, right? Now we have to do the let past time equals to now, because now should be bigger, minus last time. Okay, that we have when we clicked. So past time, so we decide about the interval of the, when we calculate for how many interval of time, millisecond, we calculate the quaternion increment. If it's greater than 20 millisecond, right? It's okay. Okay, so but we have to update the time. Last time equals to now. So that when we are calculating, we already, maybe we just do, yes, we have the time that's going on. Okay. And but also we have to update our prev x, which is x, and our prev y, which is y, right? So when we get the result, um, when we get v1 v2, we're gonna get the quaternion from v1 and v2 vector. It means cross product, but let's do the projection first. So let's set the quaternion increment equals to get quaternion vec to vec, which take v1 v2. Okay, let me getting the normalized device coordinate of current mouse location. So only the dragging through, we perform the rotation incrementation, and here we project our um, screen coordinates on the sphere. Okay, and here we get the quaternion from two the two vectors. Okay, if we get the quaternion, then we concatenate quaternion to get full current rotation current Quaternion rotation. Quaternion rotation, and for that we just set Quaternion rotation, which equals to Quaternion multiplication. So we always multiply the updated one on the right of the current one, right? So it will be Quaternion increment times the Quaternion rotation, right? Okay, so but the Quaternion has to be unit, so we have to normalize. If we don't normalize, because we know Quaternion is just a vector, normalization is the same, so we just push it because it will be vec4, so we just push it, that's it. And as soon as it's done, we just need to transform and render on canvas, right? Okay, but if it doesn't work here, we can also change it. Render. Okay, now our first job is to produce a projection on sphere, which is a function projection on sphere, and it takes v1, v2. Oops. So when we get them, we need normalize v1, which is normalize the v1, right? No. Unfortunately, this one is not here. I'm confused a bit. So we need to determine the radius of our, let's say 2, and we need also to determine the distance of our here is xy, the distance of our point from the origin, which will be the distance squared, which equal to the map, no, actually we get it from the equation of the, let's set it here, x, what is the square, x square plus y square, equation of the sphere, of the circle first, just a second. No. Okay, let me just put this one plus z square equals to r square, right? Equation of sphere. Okay, our distance from the origin to the end of the vector is equals to map the square root of x times x plus y times y, right, to get the distance. So now we want to check if the distance is less than This one is for the sphere, but also we need the equation of circle, which is like x square plus y square, which equals to the r square, right? And in that scenario, we just want to check if it lies out of the sphere circle, right? So if it lies inside, if it lies inside, which means that according to the equation of the sphere, let's let z here, let z here. According to the equation of the sphere, z equals to the math dot square root of yeah, of r times r minus of distance times distance, right? Okay. Then we just return this one. But if it doesn't lie in the sphere, it means we have to project it on top of the sphere. Oops, but we actually need to return, as I said, we need to return vector, right? So it will be x, y, and z. And we return that one. But if it's not, we need to project it on top of the sphere, which means we give z equals to 0, we just project it, and we return it, right? But with the new coordinate of x and y, which has to be shrinked to the, which has to be normalized according to the, scale. One second. But this one is in device coordinate, if I'm not mistaken, right? Let's see. Yes, we have to scale it to x equals to r. We have to scale it x times r and y equals to y times r. Scale it to spheres radius. So if we scale it to sphere radius, then we do all of this magic, right? But we already, but if it's outside, we have to rescale it again, so that it match right, if I'm not mistaken. So yeah, okay, let's let scale equals to radius. We know that we have to, because of the d, we already scale it x and y. So because the distance is more than the r, so we have to scale it down. already scale it. So okay, let's just set the distance, and we return, everything is about testing. Vec3 of x times scale, y times scale, and 0 as z, right? So we get the projection on sphere. Now the get quaternion vec to vec, which we have to create. Okay, we have quaternion to rotation, quaternion multiplication. Okay. Function. Wow, it's like takes a lot of time. Okay, let's go fast a bit. Quaternion to v1 and v2. For this one, we have to let normalized v1 equals to normalize v1. Let normalize v2 equals to normalize v2. So let's get the half angle, which will be like a math that a cos of the dot product, because we already normalize it, of normalized v1 to normalized v2, and we divide it by 2, and we get the half angle. And if we get the half angle, we just need to calculate the sine, which is equals to mod dot sine of half angle, and let cos equals to the mod dot cos of half angle. No, oh, we don't need comma, it's already there, comma. So and let the normal vector, the normal equals to which is a cross product, the cross product of v1 and v2 . Oh, I think it should be of normalized v1 and normalized v2. When we get the cross product, then we just return the vec 4 of cos and sine times normal of 0 and sine times normal of 1 and sine times normal of 2. Let's see now if we get everything done. Everything should be working properly. Now what we need to care is about how we implement now the quaternion. Okay, but I have to explain one thing here. We need now, if we get the quaternion rotation, we need to multiply the previous quaternion to the current one, and then we get the quaternion to rotation matrix, then we append into the model view matrix. But I think we forget something here. Quaternion multiplication. Okay, yeah, we already multiplied. Then okay, now and this one quaternion to rotation matrix, I get it from this Mr. Addison on this his webpage. That the formula, and there is two formula: row measure formula and column measure formula. And this formula is a column measure formula. And the quaternion multiplication is quite easy, but also I get it on Google. That's the link here. Yes, to save time. Okay, and now here. Okay, let's try to use scaling, uniform scaling, rotation X, let's comment that, rotation Y, comment, rotation Z, comment. Now let's add rotation using quaternion to matrix. Okay, model view matrix equals to multiplication of quaternion to matrix, quaternion to matrix, which use automatically the quaternion rotation to the previous model view, which has scaling factor, right? Okay, model view, and then this. Okay, let's try. Oh, there is a problem. Hello guys, welcome back. So our problem is basically we didn't specify the size here, and the size should be 4. So now we can see now we have our rotation perfectly, and we can actually even increment the rotation velocity by actually we can put velocity here, and we start by velocity of 1, and and when we are getting here, yeah, we can just put model dot velocity times this model dot velocity times this. Okay, and okay, let's see where can we increase our, okay, let's increase our velocity with because now we control by this. Let's increase our velocity with arrow up and arrow down. Here will be velocity, here will be velocity. Okay, now let's try, but now you can see it is rotating faster. If we decrease it, okay, let's choose an object, and to end, because it's quite long, AI, zoom out. Now we can rotate, perfect. Okay, thank you for your attention.